Welcome to this video on electrical measurement. Here we will discuss the Wheatstone Bridge as it is widely used in engineering applications. This video will cover what the Wheatstone Bridge is, how to derive the equations to analyze using only knowledge of voltage dividers, and an example of an application in temperature sensing. This is the configuration that is widely known as the Wheatstone Bridge. Although this circuit looks complicated, its configuration is very useful for taking electrical measurements. Circuit configurations are known as topologies. This derivation only requires a knowledge of voltage dividers, so if you haven't checked out our previous video explaining voltage and current dividers, it is worth watching first. In this derivation, we consider the simple fact that the voltage in each branch in a parallel circuit is the same. Each branch has been color-coded to make it easier to understand. All we want to know is the voltage at the node between each resistor. So the voltage divider equation can be used as shown to find this for VA and VB. Now, if you consider placing a voltmeter across these nodes so that the voltage measured is in opposite directions, thus canceling out, then Vm is equal to VA minus VB, as shown. Some simple substitution gives this final form. Here, we note that if all of the resistors have the same value, then the measured voltage is 0. So the usefulness of this circuit arises from resistor selection. To explain this point, we will consider designing a temperature sensor to ensure that the voltage measured is not 0. Suppose R4 is a temperature probe, and R1, R2, and R3 are all the same value and are thermally isolated so that they remain the same. Then temperature changes cause a change in resistance in R4 only. If we assume this resistance is R plus delta R, then by substitution, the measured voltage is related to this change by the final equation. So, by knowing the voltage measured, and if we know the physics behind how much a certain resistor device changes in temperature fluctuation, then we can work backwards to find the temperature. This last step is often done by a computer, so this is where connecting the circuit to a microcontroller and writing some code to analyze the results comes in. As such, there is an overlap between this and digital electronics. To conclude with some final remarks, this video has introduced the Wheatstone Bridge, derived equations to analyze it, and an example in real-world applications in sensors. Subscribe for more, and don't forget to check out our other videos.